Hi everyone. In a previous installment of Programming for Lovers, we learned how branching can help us make different decisions based on testing a condition. Branching is a core tenet of computer science, but another one is looping. In a while loop, if some condition is true, then we perform a set of instructions, and then we test again whether that condition is true, and we keep performing those instructions over and over until the condition is no longer true. In this installment of Programming for Lovers, we will introduce while loops in Go, and we will then apply while loops to implement a function that takes as input an integer n and that returns n factorial. As always, if you like what you see, please like, subscribe, and join our course at programmingforlovers.com. Let's code. As per usual, the first thing that we need to do is to create a file to store our code. And we've been working with this enough for me to trust you to go ahead and create a folder in Go SRC. And let's call that folder loops. And then within loops to create a file called main.go, which you can see on the left side of VS Code here in the File Explorer I've already done. And I've already also put a couple things into our main.go file. I've got some pseudocode from the main text that's going to be helpful for us. So we have pseudocode for writing a factorial function. We've got pseudocode for writing a EuclidGCD function. And I've also got some stub code that's just going to be our package main, import fmt, and then I've got func main as well, where I'm just currently printing loops. Okay. So once you have that structure ready to go, the first thing that I would like to do is to start working with while loops in this lesson and to see how we can implement this factorial function that's presented here in terms of pseudocode in Go. So let's do that. Again, here's our factorial pseudocode, and I'm just going to, at the bottom, start writing out, converting this pseudocode to Go. So I'll have a function called factorial, and it needs to take as input an integer n and returns n factorial, and we know that n factorial is equal to n times n minus 1 times n minus 2 times all the way down to times 2 times 1. And so our function signature is going to say func factorial. It needs to take an integer n, and it's going to return an integer as well. And then in terms of the pseudocode, the first two things that we want to do are declare two variables, one being p, that's going to store our final product. So we're going to keep multiplying things into p. So p is going to be equal to 1. And then we're going to have an I variable that's going to represent our counter. So it's going to keep track of what the current number is that we're going to multiply into p. So I is going to be equal to 1. And then at the bottom, after I complete my code, I'm going to return p. Okay, so this is just declaring our variables, keeping in mind what they're going to represent. And I'll just say we'll store the product and serves as a counter. And that counter is going to go through our while loop. So if we look at our pseudocode, we have the structure while I is less than or equal to n. We're going to set p equal to p times I. So I is going to get larger and larger and larger, and we're going to keep multiplying n larger numbers into p. And every time through the loop, I need to remember to increase I by 1. So that's what we want to do. The only thing to learn here is how it is that Go implements while loops. So it's a good opportunity for us to encounter a quirk of Go, which is that although it supports while loops like all modern programming languages, it doesn't use a while keyword. So we've been using the while keyword, so to speak, in pseudocode. Go is quirky in that it doesn't have the while keyword. It has only one keyword for loops, and that keyword is for. So we're going to see for is used for loops as well. But if we want to represent a while loop, we're going to think of when we see the word for, we can think of that as while for now. So what is that our while loop needs to do? It needs to check while I is less than or equal to n. And as we saw on the level of pseudocode, we're going to set p equal to p times I, and we're going to increase I by 1. So in each of these cases, we again get to see the behavior of taking the value of p on the right, doing something with it, in this case multiplying it by I, and updating the value of p in the variable on the left. The variable I is going to be equal to whatever its current value is plus 1. So that's going to allow us to multiply the current value of I into p and increase I by 1 and continue cycling through for as long as it's the case that I is less than or equal to n. As soon as I exceeds n, it goes to n plus 1, we no longer want to multiply numbers into p. So I will just add this as a comment. Go has no keyword while and uses for instead. Right? But once you've done that a few times, it'll be familiar. I also want you to notice the brackets. So just as with if statements, we use brackets around our for loops and our while loops in Go. We're now ready to call this function. So let's call our function and print a value. So let's print, for example, factorial of 5. And just make sure that everything is working. And then I can click down here and pull up a terminal. And in the terminal, it's already got me in Go in my home directory. So I just need to cd into src loops, go build, and run. And I see that factorial of 5 is indeed 120. We can verify that. So 5 times 4 times 3 times 2 times 1 is 120, which is good. And our function at least appears to be behaving for now. Let's try another value. So let's instead try, see what happens. If I plug in a completely valid integer, which is negative 100. Now you might think, well, I don't know what negative 100 is. But negative 100 is certainly, negative 100 factorial is, but negative 100 is certainly an integer. We can save this, and we can hit up a couple times to get to go build, hit up a couple times to get to /loops. And we see that 1 gets printed. So you might think, well, is that acceptable behavior? Not really, because we don't even want the user to be able to plug in a negative value into the factorial function. And so we want to start seeing how we can prevent certain activities in code that we don't want to really allow. And the way that we're going to get at that is to start having, say, error messages. And the simplest way to incorporate error messages is to use a built-in function that Go has called panic. So we can easily check for these cases of plugging in a negative integer by saying, well, that's if the input is 0, and you'll note that I am putting this if statement at the top of the function so nothing else can happen. I'm going to be checking this parameter first and foremost. And if it's negative, I want to take an immediate action. And that immediate action that I'm going to take in this case is to panic and end the program. So panic, and you're seeing, because I've got the Go package installed, I've got descriptions on these functions that I'm using, in particular panic here. I'm going to say error, negative input given to factorial. So that will give a helpful error message to the user. And when a panic function is encountered, when panic actually gets called, that message gets printed to the terminal and the code terminates. So you won't have anything else. This is as if the function returned, but the entire program is going to halt, and that error message is going to get printed to the console. So that now, when I save my code and compile and run it, you will see that 5 factorial got printed, but this panic message, error message, got printed to the console next. So the function entered this if block and panicked. So that's good. We want to be able to not allow certain types of behaviors in our code, that being a good example of one. One more that I might illustrate is what happens if we print factorial of 0. And in this case, it's not going to panic because 0 is not less than 0, so we're not going to enter that if block. And if I save, compile, and run, then you're going to see that 1 gets printed. And you might be curious, should I panic in this case as well? And this just allows me to have a mathematical aside that you might be watching this and have heard that 0 factorial is equal to 1. And I remember being taught that 0 factorial is equal to 1, and I thought, well, that's a very strange thing, because how is that possible? I'm thinking of 5 factorial is 5 times 4 times 3 times 2 times 1. How is 0 factorial equal to 1? How are there any multiplications that are happening? And I will use this aside to teach you something that I didn't learn until I was a sophomore math major in college, which is that there is a mathematical fact, which is that n factorial is equal to n times n minus 1 factorial. So for all n, you can peel away one factor, the factor of n, and you're left with n minus 1 factorial. So there's nothing earth-shattering there. But if that's true, think about what happens when n is equal to 1. Well, that means that 1 factorial on the left is equal to 1 times 0 factorial. But we know what 1 factorial is. It's 1 times itself. It's just 1. So 1 is equal to 1 times 0 factorial. And when you divide both sides by 1, you get 1 is equal to 0 factorial. Mathematical aside over. I hope you enjoyed it. For now, I'd like to come in and print one more value. So the other value I want to print is factorial of 300. So let's save that, compile, and run. And I see that factorial of 300 factorial, what gets printed is 0. And you might think, wow, is there some bug that's going on in our program? You might pause to think about what actually is going on here. I'm going to tell you, but it's worth thinking about sort of what might be happening, that 5 factorial is fine and 300 factorial is printing a value very quickly. I'll show you again. The value that gets printed is very fast. It tells me immediately 300 factorial is equal to 0. I'll give you a hint that it doesn't have anything to do with our code being wrong. It's not as if we've written an incorrect while loop or there's some bug that's floating around in our program. What we're seeing is the same type of thing that we have seen previously, which is that there's only a finite amount of storage for any integer. And 300 factorial you might think is just a product of 300 numbers, but it is an enormous number. The number of atoms in the universe is something like 10 to the 80, a 1 with 80 zeros following it. 300 factorial is a number that is much, much larger than that. And so what is happening is that we're experiencing this overflow, integer overflow again, where the numbers are getting so big that they're wrapping around and going to actually negative numbers. So you will see this if we were to print, say, factorial of 40. We'll see what that gives us. We'll get a negative number, and that's because it's wrapped around. And so eventually what will happen is you can print 45. And these numbers keep getting multiplied with all this integer overflow. And eventually what happens is you encounter a number that's divisible by the largest possible integer that you can store. And once that happens, you start to hit the number 0. And so I don't want to spend, again, this is not a mathematics lecture, I don't want to spend too long on that, but by the time I think we get to, say, factorial of 70, we're already at 0. So what I would ask you to do is see if you can figure out where that behavior first occurs, where the first point is. Maybe the first point is where factorial is negative. Maybe the first point is where factorial eventually becomes just 0. I'll give you a hint on how to solve that exercise if you want to try it. It's a great opportunity to practice a while loop. You can write a while loop in main and have that while loop range over some values, each time printing out the current value of n and then factorial of n. So try that if you like. In the meantime, I'm going to continue on. So I want to show one more thing, which is what happens if I were to forget to increase, I'm in the wrong line, forget to increase I each time we go through the while loop. So I would be multiplying p by I and updating the value of p accordingly, but I wouldn't be increasing I. So you might think for a moment about what exactly is going to happen. And I'll tell you that we're going to set I equal to 1, and then we're going to, every time through our while loop, we're going to set p equal to p times I, but we're not going to take any action on I. So one thing that's going to happen is every time we multiply p by I and update the value of p accordingly, we're just going to be multiplying p by 1. So p is never going to have any value other than 1. But the reality when we save and run is worse than this, which is that you just see a cursor at the bottom. And that means that the code is running behind the scenes and has not terminated. The program has not finished. And we know from before this program, it's just ranging over a few values of I in a normal case, and it completed very fast. In this case, we're waiting forever. And we're going to sit here and wait forever. And the reason why is because our while loop might not look like a while true, but in fact it is a while true in disguise. If I plug, I believe, n equal 5 into the function, and I call the function with n equal to 5, then what happens is I get set equal to 1. 1 is certainly less than or equal to 5. P gets multiplied the value of p times I, which is 1. And that's the only behavior that the while loop takes. So I is always going to be less than or equal to 5. I never gets incremented and never gets increased by 1. And so we're behind the scenes, Go is cycling through this while loop over and over and over and over and over again, and continuing to set the value of p equal to 1 futilely. So no real action is getting taken, but the program is running. And in this case, I can analyze that, and I'm going to use Control-C to halt the program. As we start to code larger projects, it's going to become perhaps more and more challenging to be able to have that type of meta-analysis of our code, where I can quickly say, oh, I understand that in this particular case, there is an infinite loop for this specific reason. It's not going to become impossible, but it's going to become more challenging to do that type of analysis. And you might wonder, well, is there some way that maybe the programming language itself could go in and analyze these types of things for us, do these sorts of meta-analyses and do a check on our code and make sure that we're not having some process that's going to run forever, that our program's simply never going to terminate. And that's a simple example. But the question of how can we get programming languages to determine if a program is going to halt is at the absolute dark heart of computer science. And answering that question takes us to some strange and wonderful places that we'll eventually get to much later in the course. But I wanted to point out for now, if you see the blinking cursor, or the cursor at the bottom of your terminal, meaning that your program hasn't terminated, you technically won't know. Maybe the program's about to finish, or maybe it's stuck in an infinite process. And if you simply wait, you may not be able to answer that question in a timely fashion. So these are the sorts of things that we need to keep in mind. Even though we're relatively early on in terms of learning about programming, these are still very fundamental questions that we're going to return back to. But we'll save that for now. I'd like you to try an exercise. So in the exercise that I would like you to try, and I'll put it beneath here and start this as a function comment, is to write a function that takes an integer n as input, and it returns the sum of the first n positive integers. So I'll leave this to you. I'm going to go ahead and start writing the function signature. Func sum first n integers, n int, and it's going to return an integer. And if you'd like to try that, please pause the video for now. I'm going to show the solution to this function, but it's going to give you an opportunity to practice some of the things that we've learned about, panic statements, while loops, that type of thing. So give it a go. And in the meantime, I'll show the solution for this. So the first thing that we want to do is to handle negative input. Perhaps we want to be able to plug a 0 into this function when we call it and return 0. We want to plug 1 in and return 1. We want to plug 2 in and return 1 plus 2 equals 3. But we don't want to plug in negative 100 in the same way that we didn't want to do that for factorial. So the first thing that I'm going to do is to reuse this code where I panic if a negative input is given. And so I'll just say sum first n integers here. So in each of those cases, we're going to panic. And then we're also going to want to introduce a while loop to, as we range through, add 1, then 2, then 3, then 4. So instead of multiplying by these integers, we're now going to add these integers as we go. So I'm going to, in the same way that I used a variable to store our product in factorial, I'm going to set a sum variable to store the final answer. And that's what we're going to keep updating as we go. So at the very end, I'm going to return sum. And in the meantime, I need some type of while loop. And the while loop I'm going to have is analogous to the one that we had in factorial, which is to say while, and we have to get in the practice of saying for I less than or equal to n. And here I'm going to need a variable I to represent each the current integer that we're going to add to sum. And then while I is less than or equal to n, I'm going to do the same two things that I did before, except here, when I take sum, I'm going to take sum plus I, not sum times I, and I'm going to set I equal to I plus 1 again, so that I'm increasing I by 1 each time through the loop. And that's our function. At the end, we return the sum. I'll let you call that in main if you like. In the meantime, I'm going to make a few remarks about how we can have some syntax shortcuts every time we're incrementing a variable, i.e. increasing it by 1, or we're updating a variable by saying I'm adding something or multiplying something to its current value. As you can see in both of these functions, these types of expressions are very common in programming, where we take the current value of a variable, manipulate it in some way arithmetically, and then update the value of the variable accordingly. In this case, both sum and I get updated in that way. So one of the most common types of expressions that you will see in programming in general is this type of incrementing a counter variable, setting I equal to its current value plus 1, so adding 1 to the current value. And it's so common that we don't need to continue writing I equal to I plus 1. We have shorthand that allows us to simply type I plus plus. And there is also I minus minus for I is equal to I minus 1. I'm going to add that as a comment. You might have actually heard of the programming language C++, and it's where the syntax originated, and it's an homage to the idea that there was a programming language called C, and C++ was an updated version of that language. So it was as if, instead of you're thinking of your current version plus 1, right? So it was a little joke there. But most languages have now adopted this format of I++ or I minus minus for increasing or decreasing the current value of a variable by 1. You also have expressions like what we see with sum equal to sum plus I, And this type of expression is so common that in Go we have the shorthand sum plus equal to I, where this is equivalent to sum equal to sum plus I. It's convenient if you don't like expressions like this where you have a variable on the left side, but you also have what looks like the variable on the right side. And this might seem alien for now, but in time you'll get, I think, probably very used to programming in this way. It's very convenient to use, and it makes sense. I'm going to take the current value of sum and add to it the whatever I is. And that could be a more complicated expression on the right, but in this case it's just I. You also have, I will say, you also have sum minus equal to I, sum times equal to I, and sum divided equal to I. Each of those types of expressions mean what you might think they would mean. So sum minus equal to I means sum equal to sum minus I. Sum times equal to I means sum equals sum times I, and sum divided by equal to I is equivalent to sum equals sum divided by I. All right. One more thing I would point out, which is that you now know enough about loops to implement Euclid's GCD algorithm that we have seen in the main text. It says while a is not equal to b, you have two checks. You simply take whichever value is smaller and subtract it from whichever value is larger and update accordingly. So if a is bigger than b, you set a equal to a minus b. If b is bigger than a, you set b equal to b minus a. And you continue doing this until a and b become equal. And that's an ingenious algorithm because it's not clear at all at first why it even works, but it always returns, provably, the GCD of a and b. We're going to come back to Euclid's GCD algorithm and implement it ourselves soon, but I thought for now, you know enough now to be able to implement it. So give it a go if you like. And if not, that's cool. We'll see you soon and implement Euclid's GCD ourselves. And we'll do it then. So I hope I'll see you then. I hope you had a good time. I certainly did. And until next time, happy coding.